Earthquakes are among the most intense and destructive natural forces. When seismic activity occurs, the ground that supports civilization can lose its strength and stability. This is soil liquefaction. Liquefaction occurs when intense vibrations causes saturated soil to behave more like a liquid than a solid, which inflicts severe damage to surrounding infrastructure and the communities that rely on it.
Liquefaction occurs when loose, saturated soil is shaken during an earthquake, increasing the pore water pressure and nearly eliminating the effect of stress. As the seismic waves generated travel along the Earth's crust and cause the ground to shake, the soil's resistance to shear stress lowers, particles lose contact with one another, and the soil gets softer. This results in the destabilization of particles and liquid-like fluidity. Phenomena like soil boils may occur during or after an earthquake, indicating the presence of liquefaction. Soil boils are conical mounds of sand through which a subsurface soil-water mixture is extruded. As the ground shakes, the soil is subjected to shear forces, increasing pore water pressure. This increase in pressure can drive the soil-sand mixture upward until it bursts out of the ground. After the earthquake, soil particles eventually begin settling out unevenly, causing pre-existing infrastructure to lean, crack, and collapse. Fine-grained sand was sieved, saturated, and vibrated on a vibration table in order to simulate the effects of earthquake soil liquefaction. As you can see, the can placed on top of the sample begins to sink unevenly as the sand shakes.
Liquefaction typically occurs in geographic locations with high water tables and high porosity sand and silt soils. Soils have to have large enough void spaces between particles to produce strong enough pore water pressure. Being in a location with a high water table means there will be greater saturation, total water content, and pore water distribution, increasing susceptibility to liquefaction. Liquefaction can be dependent on factors such as insufficient soil compaction, seismic amplification, grain distribution, soil density, and other geological factors. San Francisco is an example of a city at extreme risk of soil liquefaction. Large parts of the city's downtown areas are located along the coast with relatively shallow water tables, generally less than 10 feet. This is further exacerbated by the fact that several land reclamation projects occurred throughout the 20th century, depositing loosely compacted soils and increasing the amount of liquefaction-susceptible land in the city.
In 2011, a 6.2 magnitude earthquake struck Christchurch, New Zealand's second largest city. Located on the South Island, Christchurch was built upon a broad alluvial floodplain, characterized by large depositions of loose sand, silt, and gravel. The city has a relatively shallow water table, often less than 2 meters below the ground level, with the shallowest areas occurring along the coast and the banks of the Avon River, which flows through the city's eastern suburbs. These conditions make the city an ideal site for soil liquefaction, and this exact phenomenon occurred during the 2011 earthquakes. Large areas of the city experienced soil liquefaction, with the concentration being along the banks of the Avon and Heathcote rivers, highlighted here in red. After the earthquakes, it was determined that the liquefaction susceptibility in these red zones was too high for human habitation, and some 10,000 residents had to leave the area. Now the houses have been cleared, and all that remains are the empty, crumbling streets.
Geotechnical engineers help prevent soil liquefaction by improving ground stability and designing smarter foundations. They test soil and groundwater to determine density, permeability, and saturation levels, then use methods like compaction to reduce void spaces, drainage systems to relieve pore water pressure, and grouting to bond loose particles together. In high-risk zones, deep foundations, such as driven piles or drilled shafts, anchor structures into stiffer, more stable soil layers, keeping buildings and infrastructure safe during earthquakes.